So you've got this function, you want to optimize it, and trying to find all these partials with the chain rule and then setting those equal to 0, it's a hot mess. Instead, maximize or optimize the radicand. So that's a tip for you. You can use it anytime you need it, okay? Put it in your back pocket. So it's the same as maximizing this function. So I call this D for distance formula, because you're finding the distance between a point that's on the sphere boundary to our point, that they gave us. So it's the same as maximizing the radicand. So that's going to make life so much easier. Now, at the very end of the problem, we better remember when they're asking us for the actual max distance, we got to make sure we put that radical back in, otherwise we're going to get the wrong answer. But this is the quantity that we'll optimize. And then the constraint, well, where's the constraint? Does anybody see a constraint equation anywhere in this word problem?
Sphere. The sphere itself.
Yeah, this is our constraint. The point XYZ is constrained because it's got to be on the boundary of the sphere. It can't just be anywhere in space. Sure. So you know the drill. Get the constraint equation written in the proper format where everything's on one side and zero's on the other. And then that right there is your G that we're going to use when we create big L. So then this is the way I do it. My approach, I form big L, which is going to be a function of 4 variables, x, y, z, and lambda. That's the Lagrange multiplier. And I'm going to take my f, x, y, z and subtract the lambda times my g, and then I'll do calculus on that. So my L for this problem is going to look like the radicand. Oops, that's a plus.
During quizzes or exams, do you want to see that equation? Yeah,
I do. I really would like you to use my approach. That would be nice. Now, if you want to use Briggs' approach, where he just takes the gradient of f and sets it equal to lambda g, which is essentially the same thing. If you want, you could do that. I've had students who totally ignore me. Like half my calc too. Yeah. Oh my God, this semester. Okay. So there's your Lagrangian. Now what? Go get his 4 partials. I'm just going to do this pretty quick because I think you can follow this. You've seen a few examples already. I'm just doing more and more examples because I care. You're welcome. So when I find the partial with respect to x, I'm going to use the chain rule on that guy, and that derivative is 2 times the quantity x minus 1. And then the rest of these go to 0, and then I'll have minus lambda times whatever the derivative of inside parentheses with respect to x, but that's 2x. And set it equal to 0, Whatever. Then what? Then go get the partial with respect to y. Okay, chain rule again. Woohoo! Minus lambda, 2y, fine. And then get the partial with respect to z. Okay, 2 times the quantity z minus 1 minus lambda 2z equals 0. And then take the derivative with respect to lambda. Well, that's going to be negative. This constraint, set it equal to 0. And then if you multiply both sides by -1, you just get the constraint. We know. Okay, now my technique where I get my lambdas. So my lambda 1 is going to be 2x minus 1 over 2x, but you can reduce this to lowest terms and you'll just have x minus 1 over x. Okay, then I solve for lambda with the second equation and I get lambda will be 2y plus 1 all over 2y, and reduce it because the 2's cancel. And I get y plus 1 over y. Fine. And then my third lambda, these are really all the same lambdas, so I'm putting subscripts, but it's not really. 2 quantity of z minus 1 over 2z, reduce it, I'll get z minus 1 over z. Okay, now all of those lambdas have to really be the same lambda. So if I set the first one equal to, what the heck, the second one, fine. X minus 1 over x has to equal y plus 1 over y. And if you multiply both sides by xy, so what's going to happen? That's the LCD, which is the same as cross multiplying. So you reduce, and on the left you get y, quantity x minus 1. On the right-hand side, after the y's cancel, what do you get? You get the quantity y plus 1 times x, and then distribute to eliminate parentheses. So I get xy minus y is equal to xy plus x. Subtract xy from both sides, so you kill that term off. And then you end up with negative y equals x, but I like my y's in terms of x, so y is equal to negative x. Save that for later. Good news, I just got one of the variables in terms of x. I like to get everybody in terms of x's, but if you want to get everybody in terms of y's or z's, that's legit. Okay? Then I'm going to set lambda 1, equal to the third version of lambda, because they're really the same lambda. Okay, fine. And what do I have here? So when I do that, I have x minus 1 over x equals z minus 1 over z. And do the arithmetic. It's going to turn out that x is exactly the same as z. Okay, I'm skipping steps. I think you can do the algebra on your own. Okay, so now what? Well, now take these two guys and substitute into the constraint, because now you have y and z in terms of x's, which is beautiful. So your constraint is just the sphere equation. So you're like, oh, how hard could that be? So you're going to go x squared plus y squared, but y is negative x, plus z squared, but z is the same as x, equals 4. And squaring a negative gives you a positive. So these are like terms. And you go ahead and add those terms together. So I get 3x squared is equal to 4. Lovely. And that means x squared is equal to 4/3. And you know the drill. You're going to take square root of both sides. You better remember your plus or minus. Do you think I'm going to put something that has a plus or minus in a quiz or a midterm or a final?
Of course.
Oh yeah.
Oh yeah. Oh yeah. I'm like, that's one of my pet peeves. Okay. I got a few pet peeves, but I'm letting you in on some of my secrets. This one, when students are solving an equation and they take an even root of both sides and they forget their plus or minus, because when I teach differential equations, that's also a big deal. I just kill them. I put on all my quizzes and all my exams. So by the time they leave me, they have it. Oh, back to that. Ooh, that was just too cool. So what do I have for my x? So my x coordinate, notice I'm going to get two different x coordinates, and this should peak in your mind, perk you up. Remember, we were looking at finding a maximum distance from the point to the sphere boundary. So one of them might give a max and the other one a min. Now you have to be careful here. The reason why I'm doing this problem, because a lot of people are going to get excited. Oh, that's the same as the other one where y could be plus or minus x and z could be plus or minus x. No, this is not that. Our y is different from that problem I did on Monday. This y says y has to be exactly the opposite of x, not plus or minus x. Big difference. So we don't have like 8 different critical points in this problem. So how many critical points do you think we're going to have? Because I claim, you know, now that you know that x is z is the same as x and y is negative x, your critical points are
critical
what?
points.
You should have only 2.
You're
You
gonna-
have 2 only. Good. And what are they?
So depends on what you want to use first for your plus or minus.
Okay, how about x is positive 2 over square root of 3? So what are my other coordinates?
All right.
Negative
Then-
2 over square root of 3.
Mm-hmm.
Mm-hmm.
Same as, and then the z would be the same as the x.
Right. And then my other critical point?
Negative 2 over radical 3.
Mm-hmm.
Positive 2 over radical 3.
Mm-hmm.
2 over radical 3.
Remember, z and x have to be the same.
Oh, my bad. So negative 2 over radical 3.
Yeah, okay. Those are the only 2 critical points we have. That's it. Well, the problem wanted the max distance. Oh, well, don't guess. How are you going to figure out which one of those is the max? Well, you could do it kind of visually, you know, like if I did do negative, positive, negative, I think that one's going to get me here. And then if I did go positive, negative, positive. It's hard to say. Yeah, I think that would give me the min. So the way to do it analytically is plug it into the original problem. Which one? Well, remember your fxyz is giving you the distance, and I don't want to put the square root yet. I'm just trying to figure out which one is going to give me the min or the max. And so, you know, you're going to plug in the points. I'm just going to tell you which one gives the max. This one is going to end up maximizing your distance, and this one is going to end up giving you the min distance. So if they want the max distance, after you plug this in, so you're going to go -2 over square root of 3 minus 1 squared, plus 2 square root of 3 plus 1 squared, plus -2 over square root of 3 minus 1 squared. So you punch
Bring
that
that
out,
here.
and then you square root it. So your distance, remember, is the square root of this. You will get, I think it's approximately 3.73. That's your max distance. And then you can find the min distance by doing a similar thing, plugging in your min. Okay, questions?
How did we get 8 critical points?
How did we get 8?
Why were there only 2?
Well, in this problem, which is different from last time, do you remember last time? Go check your notes because I don't feel like scrolling. But we got y could be plus or minus x, and z could also be plus or minus x.
Oh, okay.
But we don't have that case here. In this case, y is exactly -x only. And z is exactly the same as x. Z doesn't have a, oh, it could be plus or minus the x. Z has to be exactly whatever x is. Do you see the limitations here?
Okay, that makes sense.
Okay, just chew on it for a while. If you're still a little bit strange, then stay after class. We can iron it out for you, okay? So this one only has 2 critical points. So the reason why I do this in lecture is I want people to see the difference. Like plus or minus means something different from just negative. Okay, so now I want to step down a notch. Usually I like to kick it up a notch, but I'm going to step down a notch. What? Yeah, we actually did the harder Lagrange the first half of this lecture. Now we're going to kick it down and do not as hard. Well, what do you mean? Well, what if you're trying to maximize or minimize a function of 2 variables only instead of 3 variables? Now, you have some options to do this. So let's talk about what you already know how to do. So if you are trying to maximize or minimize a function of 2 variables subject to a constraint, what you could do, well, actually a Calculus 1 student could do this, because after you have your fxy, you could solve this for y and then substitute it into the original function you're trying to optimize, and then you'll have a function of 1 variable only, and then go do Calc 1 on it. And you know how to find maxes or mins in the world of Calculus 1, right?
Yes.
I hope so. Okay, so that would be how you could do it the Calc 1 way. You know, and the other way would be, you know, go find the critical points and know that you have a constraint and do all that. But we do have a constraint, so doing it the Calc 3 way, if you do it the way I've taught you so far, your Lagrangian that you're going to form will be a function of 3 variables only, because z is not in this at all, x, y, and lambda, and you'll form it by taking the quantity you're trying to maximize or minimize, and you'll subtract the product of the Lagrange multiplier lambda with your constraint function, and then go extremize that guy. Get the partials, set it equal to 0, get some critical points, figure out the max or min. So we're going to do another distance problem, because these are classic. Like, you will have these. They're everywhere when you see these kinds of problems. So we're going to minimize the distance again, but we'll do it in 2D. So here we have a parabola. Okay, we all know what a parabola looks like. There it is. Lovely. And the point 0,3, which is right here, we want to minimize the distance from this point to the parabola. So, well, what about 0, 0? Well, is that the min? I don't know. That distance is clearly a 3, right? We're 3 units away from the parabola. Is that the minimum distance, though? I claim it isn't, and I claim by symmetry there's going to be 2 points on the parabola that have the same distance away from the point 0, 3. They have the same distance there. And so we're going to actually find the coordinates of those 2 points that give us the exact same. So it's not going to be like one's a max and one's a min, like that last problem we did. They're both going to give us the same distance, okay? A little bit different flavor here. So once again, we're going to use the distance formula, just like we did in the last problem, but we're going to use the pre-calc version of distance formula because we're in 2 dimensions. So what is the distance between these 2 points? This point, I don't know what the coordinates are, so I'm going to give them arbitrary variables, x and y. And so the distance between the xy point and 0, 3 is the square root of the sum of the squares of the distance, the differences between the coordinates. Okay, and then again, you get for free this cool fact I gave you, that maximizing or minimizing a square root function, it can be accomplished by maximizing or minimizing what's under the radical. Much easier. We don't have such crazy partials. So minimizing instead what's underneath the radical. So if I clean it up a little bit, because x minus 0 is just x squared. So we're going to call this fxy here. We're going to minimize this function. Okay, so my Lagrangian function that Dr. Vallone would teach. Dr. Vallone was an electrical engineer turned into math professor. He had quite the story. He was great. And he loved differential equations.
Is he the guy that convinced you to switch?
No, I didn't know him when I was an engineer. I just, when I started my master's program at San Diego State, I met him. He wasn't my teacher then, but I would talk to him, and he was a funny guy. Everybody liked Dr. Vallone. He was the kind of guy who would, this was illegal on campus and still is, but he'd come to his office hours and he'd crack open an old bottle of bourbon and pour you a drink.
Oh, that's awesome. I bet you need it though at some points.
Well, the sad story there is that he ended up getting a bad case of gout. I don't know if you guys know what gout is.
Oh my, really?
Mm-hmm.
Yeah,
Which is
Dan.
considered
Terrible.
a rich man's disease because the King Henry VIII had it back in the day. But it's where your big toe gets really painful and like it's awful and it hurts and they start making you cut back on your diet because supposedly a diet high in meats and fats gives you gout, although that hasn't been fully understood. So, you know, he had to give up his beer and his bourbon and he was pissed. Poor guy. Yeah, the king's disease, Chris. That's exactly right. Yeah, but Arnie wasn't really a king in that respect, but he was a king in my heart, and he died of lung cancer, and it was terrible.
Man.
Cancer sucks.
Yeah, it does.
Everybody talks about COVID being bad. Sorry, you know, COVID's bad. Cancer much worse. Like if somebody said, hey, here's a choice, COVID or cancer. I've had cancer, so I can tell you. I'll take COVID over cancer. You could quote me on that. Okay, what do I put here?
Parabola.
Okay, so what exactly do I put? Like, do I put x squared?
X squared minus y.
Yeah, see, so you got to be careful here because this is your constraint equation and you want to rewrite it where you get everything on one side and 0 on the other. And that right there is your g of xy. So be careful that you don't blow this. Like when I say get everything on one side, 0 on the other, and you're like, well, it works because I didn't get, you know, it's a constant on the one side. So I didn't bother, but it may not be. So you're going to put y minus x squared here. Okay, now what? Go to hand-to-hand combat. Get your 3 partials this time, not 4, because we don't have any z's in this particular function. Nice. And what do I get when I take the partial with respect to x? I get 2x. That's it for that. And then minus lambda times, and the derivative of y minus x squared with respect to x is negative 2x. And we'll set that equal to 0. And then get the partial with respect to y. I'm going to use the chain rule. 2 times the quantity y minus 3 to the 1 times 1. Okay, minus lambda times the derivative of y minus x squared with respect to y, but that's just 1, and set that equal to 0. And then, and of course, take the derivative with respect to lambda. That's just going to be negative the quantity y minus x squared equals 0, and that's the same as your constraint. Fine. Now, this problem is going to be different. So I hope that you didn't fall asleep, because if you already like, I know how this is going to go, I'm taking a break. I feel sorry for those people. Because solving for lambda is not going to work. Well, it worked on every single problem you've done so far. I know. And it won't work every time. And the same is for the My Math Lab. So don't be coming to my office hours with tons of tears and, oh, you know, Professor, you told us the lambda thing would work every time, and it ain't working. And I'm going to go, I told you to expect that it may not work. Okay, so how do you know it's not going to work? Well, you can go, hey, I'll start by trying to solve for lambda. Fine. So if you add lambda to both sides, you'll get this. And then assuming x isn't 0, otherwise you'll be doing yourself a disservice. And let's divide by negative. And then reducing, what do you get? You get lambda is actually a constant. Oh boy, that's a red flag for you. Now what? Well, okay, if I solve for lambda here, I get lambda is equal to 2 times the quantity y minus 3. So which one is it? Well, if lambda is equal to -1, which is what we got first, and you plug it into this equation for lambda, you're basically saying, okay, the 2 lambdas are equal, and then what do I get? -1/2 is equal to y minus 3, add 3 to both sides. I get y is 3 minus 1/2, but that's 5/2. Okay, and it turns out that you can easily get the x because y is equal to x squared, and so that means x is equal to plus or minus the square root of y, and then that means that x is equal to plus or minus the square root of 5/2. So folks, the points, and you have 2 critical points, square root of 5/2, 5/2, and negative, oops, sorry, that should be a, my bad, sorry. And the other point is negative square root of 5/2, 5/2. And one is not a max and the other one's not a min. It doesn't work like that. Both are the answers. Both give a min distance due to symmetry. Now, remember I said, hey, are these 2 guys really the minimum? So if you look at the little graph I drew up here, remember we were talking about, hey, you know, these points are over here, but are those the distance, the actual distance, really less than that vertex? Because we were kind of guessing, hey, it looks like the point 0, 0 might be the closest guy. And it turns out if you actually plug either of these points into your function, you will, you know, either one, because it doesn't matter when you square a negative. So you're going to go get x squared, which is square root of 5/2 squared, plus y minus 3, the quantity squared. And I get 11/4, and then the actual distance is the square root of this function. Remember, we looked at the radicand. And this is a square root of 11/2. It turns out that square root of 11/2 is less than the 3. You could check me out on that. So the point 0, 0 isn't the minimum. These guys are the answer. Okay? Questions?
Oh, so to get the actual distance, you need to first plug it into the one you squared and then take the square root of that.
Yeah.
Oh, okay.
Because that's the actual distance formula, right? You know, the actual distance between the points is this right here.
Yeah, because I was almost tempted to plug it back into the original distance formula at that point.
Well, that's what you want to do. You do want to plug it into the original distance formula. I essentially did that because maybe you didn't, you were not paying attention. First, I plugged it into the radicand, and then I took the square root of that to get the actual distance.
Ah, yes. All right.
You see it there?
Yep.
Okay, so I'm doing it to the original distance formula. I just did it in 2 steps instead of 1. Yeah. Okay, now for my grand finale. Now, I used to not do this problem. I used to just give it on my math lab, and then I had even my A+++ students coming to my office hour and crying. And I'm like, oh, man. Okay. So what I decided to do is go ahead and do this problem. I took one of my math labs and stuck it here in the lecture. Okay, you might even see this problem in your my math lab. So here you go. This is my gift to you.
Thank you.
So to avoid the tears, so you're not going to want to set the lambdas equal to each other here at all. It's not going to work. It's tricky. Okay. So first up, if I form my Lagrangian, in this case it's of xy lambda, there's no z's here. So I'm going to take my fxy minus lambda times g of xy, where g of xy, if I rewrite this where everything is on one side and 0 on the other, because that's how you want to get it, you got, this is essentially your g of xy. Okay, so now here's your Lagrangian. Oops, I'm having trouble writing to you. Okay. So you're going to go 4x squared plus y squared minus lambda times the big old constraint. And let's do the partials on this. So Lx is 8x minus 2 lambda x. Set it equal to 0. Ly is 2y minus, minus lambda times 6 plus 2y. Okay, set that equal to 0. L lambda is what we think it is. It ends up being the same as the constraint, but that's going to be coming into the conversation here, so you'll see. This is a really different strategy. Okay, so first you go like, oh, what can I do here? You don't want to solve it for lambda because it won't kind of get you where you want. You'll end up kind of in a brick wall. So what I did here is I factored and applied the ZPP. And I'm telling you, the ZPP will save your butt on many occasions. So if you'll notice that 2x is a common factor to both of those terms, fine. And then when I factor out a 2x, the other factor is 4 minus lambda. Okay, fine. Then what? The ZPP says that sometimes something equals 0, the first something equals 0, or the second something has to equal 0, or they both do, fine. So one of the possibilities I get is x is equal to 0, or lambda is equal to 4, okay? So what I'm going to do is I'm going to substitute lambda equals 4 into the other partial, Ly. Because if I do that, since this Ly only has y's in it, I'll be able to get a y coordinate. Okay, so what's going to happen here is I'll go, okay, 2y minus lambda, but we're substituting a 4, times the quantity 6 plus 2y equals 0. Okay, so if I distribute this -4, what do I get? So it looks like I get minus 6y minus 24 equals 0, which tells me that 6y is equal to -24. And when I reduce after dividing by 6, I get y is -4. Now here's a common student error that just, you'll choke. If some people go, oh, I know. The critical point is going to be x is equal to 0 and y equals -4, right? No. Not even close. Remember, when we found this y equals -4, we were saying that lambda was 4, not x is equal to 0. So just as a little key that you get here, the critical point is not 0, -4. So be careful you don't start forming critical points that have no business being critical points. Now here's the part that's weird. You're going to plug this x equals 0 into your constraint. Now normally the way I've shown you is you wait to use the constraint till the end when you have everybody in terms of x's, but we don't have that here. We're just going to bring the constraint into the situation right now. Okay, so if I plug 0 into the constraint, x equals 0, what does my constraint look like? It'll look like 0 squared plus 6y plus y squared equals 16. Well, that looks like a quadratic equation, and if I get everything on one side by subtracting 16, I could use the quadratic formula. That would work, although that's overkill. Well, what do you mean? Factor and use the ZPP. I claim this is a nice polynomial that factors quite beautifully. Does anybody see it?
It's gonna be 8 and -2.
Mm-hmm. And so now you apply the ZPP, and that tells me if something times something equals 0, I can set the factors equal to 0, and I get two possibilities for y. I get y could be either -8 or y could be 2. So what does this tell me now? What do I have? I actually have some critical points. I have when x is 0, y could be -8. That's a critical point. But I also have when x is 0, y could be 2. Now, the danger is some students get so excited, like, woo, I'm tired. I'm done finding critical points. See ya. No, you're not. There's more. In fact, there's 2 more critical points besides these. Really? Well, what are you talking about? Well, the other 2 are going to come from when y is -4. Remember? Did you forget about y being -4? So you're going to substitute y equals -4 into your constraint. Ooh, okay. So when I do that, I'm going to get x squared plus 6 times y, but that's -4, plus y squared, but that's -4 squared equals 16. Ooh, okay. And then what do I have? I have x squared minus 24 plus 16 equals 16. And then you can kill off the 16s and add 24 to both sides, and so that you get x is equal to plus or minus, there's that plus or minus thing again, love it, square root of 24. Well, and square root of 24 can be simplified because it's 4 times 6, and 6 is a perfect square, and so plus or minus 2 radical 6. Okay, now what? So the other 2 critical points, so more critical points, 2 more. You have when x is positive 2 square root of 6, and then y is -4, and when x is -2 square root of 6, and y is -4. So now you have 4 critical points total. That can happen. So then what? Well, hell, you don't do the d-test. What do? Because my math lab is going to ask you, you're going to do all this work, and they're going to only have 2 fields for you to type in. They're going to have you type in a max value, and then another field in my math lab for you to type in a minimum value. And they probably won't even ask you for the critical points. You may get lucky. I don't know if they do. It depends on the problem. So what are you going to do? You're going to plug them in. Plug them into what?
Our original f of x.
Yeah, you're going to plug into your original f of x, and you're going to figure out which of those 4 gives a maximum, and then just say what the maximum is, and then which of them give a minimum value, and give the minimum. So you're going to do trial and error. It's going to be a pain in the butt. So by trial and error, by plugging into the fxy, you will figure out which are the max and which are the min. So it's going to turn out, I'll just tell you the answer, what it is. It's going to turn out that these guys, or this one right here gives the absolute min. He's the guy. And the actual min value, f evaluated at 0.2, is equal to a 4. And then which one of these puppies gives the max? I think this one here, I think both of them maybe, because it's x squared plus y squared. I think they both, because of the square, both of them give an absolute max. Both of these guys give an absolute max. And what is that absolute maximum value? Well, f evaluated at, let's just plug in 2 square root of 6 -4. You're going to have 4 times x squared plus y squared and it turns out it's 112 is the maximum value. So when you're typing into MyMathLab, you're going to do all this work, and you're like, ah, and you get 4 critical. Well, what about the other critical points? You know, where I think there's one that's sort of not anything. Well, you know, he didn't turn out to be helpful. He wasn't a max or a min. What is he? Don't know. Go use a computer system to see that. Yeah.
In our work, is it okay if we would just write f of 0, 2 equals 4? Or do we have to show plugging x and y into
Well, it'd be nice if you could show plugging it in, but you know, if you're in a real hurry, I'll be okay if you just zap it. But show me, you know, what you're doing, so I know how you got it. Don't just go, well, max value is you know, 4 or min value is 4, and be like, how'd you know? So show at least one intermediate step, okay? Okay, questions on this one. This one is like pretty hard because it involves a lot of, you know, you get something and then you have to plug into your constraint to figure out the corresponding other coordinate, and then you get all these different critical points, and some of the critical points may not contribute to your max or min values. You figure it out by trial and error. Pretty weird, huh?
Yeah.
Some of the previous problems, when you solve for lambda and you divided by a variable, we assumed that variable didn't equal 0. For this problem, we would have lost information.
Right?
Okay.
Right, because like if you divide, like let's say this equation right here, like I'm up here, 2x times the quantity 4 minus lambda equals 0. If you had divided both sides of the equation by x and go, well, x isn't going to equal to 0, I'm good, I'm safe. And it's like, ah, you just killed off a big piece of information.
Okay, I get it.
That's what I did in when I came across this problem in the MyMathLab step, and oh man, that was a headache.
Okay, so do you see here that it wasn't the 0.00 that was a critical point, but for these 2 critical points that we got here, x was 0 and y was never 0, but you have to be careful because you could be into the danger zone, right? Now, if you're doing a real live problem where, oh, you know, your x is representing a width or a length or something like so, you can kind of get away with, well, I'm going to just assume that my x and y or whatever aren't 0, because, you know, that wouldn't even be a box or whatever is the dimension.
Impossible.
Yeah, you know, it's no longer a box. It's like somebody crushed it. So this is my favorite meme. I'm sorry. I'm easily amused. Okay. So questions? Any other questions or?
Good.
Okay.
I'm good too.
You guys, are you guys there? You got a lot of people.
I'm good.
Yeah, we're still here.
Yes.
Kind of, maybe.
Are you still awake, or you know, maybe when you're working on your you know, on your homeworks, you might feel like this guy, you know, stuck in prison and you know, growing a beard or in quarantine or whatever. What year is it? I finally finished it.
I fell asleep half an hour ago.
Yeah, well, when I teach differential equations, if you thought that problem was involved, and yes, it was. I mean, look at all this crap that we did just to solve the one problem. I get it. Take differential equations, because one problem might take you like 3 more pages to complete. And so what I did is, when I found this mean for Lagrange multipliers, I went to the mean generator and I generated the same mean in my differential equations course reader, because I think it's more apropos.
Would this 3-page problem perhaps be related to reduction of order?
Reduction of order, that's more of a 2-pager. I was thinking more of a humongo Laplace transform one.
Oh.
Where you have to do multiple partial fraction decomposition just to do one problem. Those can take like forever and a day. So yeah. Another type would be, and I don't know, some professors don't teach higher order DEs, but I do. Like I might give you a 5th order DE where you use undetermined coefficients and your forcing function is from hell. That might take, because you have like, you know, 5, 6, 7 unknowns. It might take you forever. Okay.
I just had a heart palpitation.
I see you like the magic meme on the course reader. Where is that, Nicholas? What are you referring to? How you solve math problem?
It says components of a calculus problem. The
Oh,
majority of the graph is magic.
yeah. Yeah, the majority is magic. We just showed that to be true, right?
I think it's funnier in grayscale. I can't tell if the big one or the small one's.
Well, it's whichever one works for you, right? That's what I would say. Okay, so we're officially done with Lagrange, and we're officially done with Chapter 15. Congratulations. You are
Wow.
halfway done through your multivariable calculus module. How does it feel? Thoughts?
Good. Fast.
Okay.
We got here fast.
No, not really. Other calculus classes are way ahead of us. We're behind.
Our speed is unmatched.
Yeah. So Isaiah, you like this one the best so far, huh? Okay. Well, that's awesome. But now I think it might even get better for you. So better things are coming. Okay. Because we're going to start doing double and triple integrals right now. Aren't you excited?
Thanks, Isaiah.
Yay!
Woo.
All right. We're going to Sizzler. Wait a minute. Did Sizzler close?
Problem.
Yes.
Yeah. Oh, shoot, man, I'm screwed. All right. Wow, all my favorite restaurants are closed. My favorite salad bar, Soup Plantation, down the toilet.
I'm still not getting over the closure of Soup Plantation. That's
I'm
a
still
real tragedy.
really. I'm in a 6-month
Wait.
depression myself.
You didn't hear, dude? Soup Plantation closed down, and ever since then, my life has not been the same.
Oh my God. Oh,
I'm sorry.
Pretty upset about Chuck E. Cheese going bankrupt.
oh my.
Oh yeah, Chuck E. Cheese
When
is
is the
right.
last time you've been
Wait
to
a
Chuck E.
minute.
Cheese,
I-
though?
Last time I did my
Isn't
drug deal.
that for 8-year-olds only? Wait a minute. Don't you have to be in 3rd grade to go to Chuck E. Cheese?
It's where you can be a kid, all right. And sometimes you want to recapture the
Aw.
this feeling of youth. The
Oh.
dirty carpet, the creepy animatronics, stuff like that.
Let me
But
have
half
this.
of the machines are broken, though.
Ooh, right. Yeah,
The weird fake roller coaster ride.
Does anybody remember the one in National City where the machines were always broken and then they would randomly turn on and just creep you out?
Ooh,
Oh, that's
Oh,
kind of weird.
that's an actual FNAF plot.
I never went to Chuck E. Cheese even when I was a kid. I think I went one time because somebody had a birthday party. So I'm not familiar. I'm probably going to date myself now, but does anybody remember Farrell's ice cream store? Farrell's ice cream parlor?
No.
I haven't heard
okay,
the word
never
ice cream
mind.
parlor in like this century.
No, tell us.
What's that? 21st birthday at Chuck E. Cheese? God, Nicholas Gonzalez. Well, you could if they're still open.
You
but,
can drink beer at Chuck E. Cheese, so I guess.
Yeah, you
Oh,
may
you
have to
can?
sneak in your own
Yes.
spirits. Let's just put it that way.
I once read this Vice article that for some reason Chuck E. Cheese's were on the rise for violent locations. Like statistically, police calls happen at a Chuck E. Cheese more than any other drugstore in a lower income neighborhood for some reason.
Yeah.
I mean, whatever. Is there a smoking area?
Called outside and the ball pit.
The ball pit!
I can see 3rd graders, over in the corner, lighting up. Okay, guys, enough fun. We got to get to it, but we'll have to have
Enough
a party
fun. Back
after
to calculus.
If we make it through this semester, we'll all have to get together and have a big end of final exam party or something. I don't know. Over at David's house, right, David?
What?
Or a vacant Chuck E. Cheese.
Sure, of course.
Oh, a vacant Chuck E. Cheese, even better. All right, yeah, it's boarded up. We'll just break it down and go in and take over. I'm not advocating this, by the way. I know we're being recorded. Okay, so let's do a prep example. I'm going to start off with like a Chuck E. Cheese example first for 3rd graders, and then I'll kick it up because you're not ready to see a double integral yet, okay? So let's do the Chuck E. Cheese version. Yeah, we're going to crash David's apartment. I don't know. There's no room there. So we're not going to do double integral, but here's the plan. I want to just set it up with, let's take a partial derivative. You know, let's say that that's a partial derivative, and we're going to go backwards. What do I mean by go backwards? Well, you know how to take a derivative, a partial. You hold one of the variables constant, and then you differentiate with respect to that variable. So integration, double integration and triple integration involves the same thinking, but the reverse. So you're going to integrate 2xy, but with respect to x. So that's what the dx means. W period, R period, T period. That's short for with respect to x. So you're going to hold y constant, and you're going to integrate with respect to x. And so I hope that you can see that you'll, y is just a multiple, so it goes along for the ride, and the integral of 2x is x squared, and you're pretty much done. Of course, you're going to have like a plus c, but we're going to say c of y, because that might not be a pure number, that because we only partially recovered the integral of 2xy, we might have, you know, extra y's in there because we didn't do a dy, okay? So we only did a partial recovering of the function. You can also do definite integrals. In fact, we will. So let's do 2xy dx where there's limits on the integral. Now you may be kind of freaked out right now because you'll notice that one of those limits has a variable in it. Is that legal? Oh yeah, but there's rules and regulations as to what the variable can be. So I think we already integrated this 2xy with respect to x. I'm just going to copy down our result. And then we are going to evaluate at the limits 1 and 2y. So the fundamental theorem of calculus says first you have to plug in the upper limit. Now here's the trick question. When I plug in that upper limit, which is 2y, do I plug it into the x or do I plug it into the y? Or does it matter?
To the x.
To the x.
Good. How'd you know?
You're integrating with respect to x.
Very good. So you're going to go 2y in place of the x and minus, and then you'll plug in the lower limit. And again, that also goes into the x. And then if I clean this up a little bit, it looks like 4y cubed minus y. Okay? And we're done. That's the answer to that problem. Okay. So we still have training wheels on right now. You're not ready for a double integral yet. We're still doing training wheels, prep examples, you know. When I learned how to ride a bike, my dad got some training wheels. I had one of these Schwinn girls bicycles. They probably don't even make them anymore. And he put training wheels, and I had a good old time with my training wheels for like months. And then finally one day my dad came home from work, and he goes, I'm taking the training wheels off. And I went, no! And he went, yes. And he took them off, and I freaked out. But lucky for me, he was there, and he pushed me, and I went, and then I fell down. And then there you go.
Did you say you had a Schwinn?
Yeah.
Wow. Really?
Yeah. Schwinn bicycles. You could probably get one on eBay.
They're still
Okay.
good.
They're still good. Okay. Not the one that I had with a long banana seat and a basket with flowers. Okay. Here's what's meaningless. If I put a limit on this integral that has the same variable that I'm integrating with respect to, that's meaningless crap. Please know this, because you are going to very soon be setting up your very own double and triple integrals. And if you accidentally violate one of these rules when you set them up, and you put a limit on an integral that matches the variable of integration, that's meaningless junk. Don't do it. Okay, let's do another prep example, and then we're almost ready to take the training wheels off, and you can ride the bike. Okay, so we're going to integrate with respect to y now, just to be different. So check out this expression that we're going to integrate with respect to y. That means you're going to hold x constant. Yeah, so x looks like a number. So when you integrate the first term, 2x squared is just a constant multiple, so copy it down, and then you're really integrating y to the negative 2 with respect to y. But I believe that's y to the negative 1 over negative 1, and I like you to rewrite your stuff with positive exponents because it's nicer. And so you're going to have negative 1 over y, so that's going to be right there, and then plus, and then when you integrate 2y with respect to y, it's super easy. What is it?
Y squared.
Okay, so that was not hard. Now, you're not done because this is a definite integral. So don't put plus c or anything like that. You're going to put brackets around here, and you're going to evaluate it between the limits of 1 and x. So you're going to substitute x in, and where do I substitute my x? In x's or y's?
Y's.
Mm-hmm. And then I'll substitute my lower limit in. So that's a 1. Mm-hmm. Oh boy. Okay. And then what is this mess here? After cleaning it up and reducing to lowest terms, I'm going to get negative 2x plus x squared. And then I think this is going to be plus 2x squared and then minus a 1. And I'm going to add like terms, make it look pretty. And so my final answer is 3x squared minus 2x minus 1. Okay, and that's the answer for that other prep example. Okay, fine. Now what? Now you're ready. Ready for what? Ready for the real deal. Congratulations. Your very first double integral. And I feel honored to be part of your very first double integral experience. Cool! Or as Nick would say, Nick S, that is, cool. No, was it not you, Nick? Who was it in our math 135? I think it was a guy named Matt. He was like, cool beans. You were like the awesome sauce dude, right? And then I said, well, what would awesome sauce taste like if you put it on cool beans, right? Pretty good meal. Okay, so now check this out, people. Your very first double integral. Woo-hoo! Congrats. Now, they call this an iterated integral. I know. I want you to learn the, it's also known as a double integral, but it's also known as an iterated integral. So how do you do this? Like, how would you do it? Well, the idea, and before I take your training wheels off all the way, is when you see a double integral, after you freak out, know that you always want to work it from the inside to the outside. So you want to go into the inside layer first. So if I put brackets here, just so you can see what I'm talking about, you actually have to evaluate this first. And then when you're done evaluating the innermost integral, then you can go to the outermost integral. And this is going to be true for triple integrals as well, because you're going to do triple integrals also. So you'll first do the innermost integral, then you'll do the middle one, and then you'll do the outside one in that order. And don't do it in reverse, because you'll end up in a world of hurt. So we'll do the inner integral first. But wait a minute. Doesn't that inner integral look familiar? Didn't we already do it up here?
Yes.
So I claim we already did that. Cool. So I don't want to do it all over again, because then I'll just waste valuable time. I mean, you can if you want to for practice. So what I know is I still have the outermost integral, and this stuff goes over here. And I did that. I got what? 3x squared minus 2x minus 1. And then the variable of integration for the outermost integral is dx. Well, it better be, because we're almost done. And then right now, this is a calculus 1 problem. You learned how to do these in calc 1. Cool. This is easy to do. We'll finish it up. You're just going to get the antiderivative as x cubed minus x squared minus x. And you'll evaluate that between the limits of 1 and 2. Fantastic. Yeah, and irritated. And I'll just skip to it. I get 3. And that's your final answer. Okay? So let's go over the rules and regs for iterated integrals, because you're going to be making your own. When you create your own double integral, which you may be asked to do on many occasions, you want to follow these rules, because otherwise it'll be in trouble. And I already mentioned what one of them is. The limits cannot match the variable of integration. So if you're doing the inner integral, the inside limits, they can be variable, but only with respect to the outer limits of integration. With respect to the outer limits of integration. So that's one rule. And then the second rule is the outermost integral. So for double integrals, it's the very first integral symbol you see. These numbers have to be pure numbers. They're not allowed to be variable. So the outside limits of integration write this down. Oh, speaking of writing down, I posted all your lecture notes over the past few weeks. So if you open up like the last 3 weeks of module, I think week 5, 6, and 7, you'll see lecture notes in there. And so I posted our lecture notes for people who feel like maybe they didn't take very good lecture notes. They're available. Must be constant with respect to both variables of integration. And so for a double integral, you don't have any choices. They have to be pure numbers, okay? And those are the rules. And Briggs, I don't think, does a really good job of making those rules clear, but I just want to. So what can you use a double integral for? So I have a little bit of time. So, so the answer to that is take the rest of this semester. Take the class, because we're going to use double integrals for a lot of stuff, okay? Yeah, I could go on. There's a whole list of things we're going to use it for. But let's start off easy. The easiest application of a double integral is you can use it to find the area between curves. Now, if you're a thinking student, you may be thinking, that's dumb. We already use a single integral from Calculus 1 to find area between curves. Why would I need to make it more complicated and use a double integral? That's really dumb. And then I would agree with you. However, you have to know this version of the application in order for us to extend and do much more difficult things. So let's just start easy. Good news, I'm going to do a quick Calc 1 review. What's my review? How to find area between curves. Really? And you may have already forgot anyway, so hey, good review. So there were, the way I teach this when I teach Calc 1 is I draw a curve here, I'll call this curve y equals f of x, and then I draw another curve down here, and I'll call it y equals g of x, say. And then I'm like, hey, kids, what is the area between the two curves? And so hopefully you remember that the area between two curves from Calculus 1 was the limits going from A to B. And you do the taller minus the shorter. Do you remember that? Taller minus shorter?
Yes.
And that's it. That's Calc 1. I'm done with the Calc 1 review. Congratulations. Okay. Now, I'm not going to do any Calc 1 problems. You go do that on your own. Now, how would you do area between curves using a double integral? Which I know seems like really complicated and like, why would I do that? And we'll see next time more reasons. But so here's the derivation. Look at the inside of your Calc 1 integral. Just the difference, f of x minus g of x. Just consider this for a moment. I claim that I can represent that expression by an integral. Well, what do you mean? If I create an integral where the integrand rather is just a 1, and I integrate with respect to dy, and the limits on the integral are going to be variable. Like the lower limit will be the shorter function g of x, and the taller function f of x will be the upper limit of this integral. Really? Well, let's just do it. Like, what is the antiderivative of 1 with respect to y? Let's integrate. Anybody know? Yeah, just y. And then you're going to evaluate y between his limits. And his limits happen to be these variable expressions. Lower limit is g of x, upper limit f of x. Okay. And, fundamental theorem of calculus says, hey, evaluate at the upper limit first. Fine. And minus and plug in the lower limit. Fine. So do you see that in your Calc 1 formula for area between curves, if the integrand is replaced by this integral, you can now do the Calculus 3 version of area between curves, combining this knowledge. You're still going to have the outermost integral, where you have pure numbers as limits, a to b, and you'll have that one be with respect to x. And then the innermost integral, which we just did, is the integral basically of 1 with respect to y, where the shorter function is the lower limit and the taller function is your upper limit. And this is a double integral that represents area between two curves. Pretty cool, huh?
Yeah.
All right.
Yeah.
So I'm going to just stop there and leave you with that thought. And we're going to pick up this on Friday and do tons more examples. Now, I want to say something before I kick everybody out and stop the lecture. I'll stop the recording here, but